In late 2022, it seemed like the entire internet was talking about Ozempic. Google searches skyrocketed, the hashtag Ozempic got hundreds of millions of views on TikTok, and pharmacies across the United States struggled to keep the drug in stock. By the end of the year, the FDA formally declared shortages on most of the major GLP-1 receptor agonists, the class of drugs that includes Ozempic. But most people don't realize that the origin story of GLP-1 analogs was one of the wildest science stories in modern drug development. Like, I read about venomous lizards and deep sea creatures and amphetamines for this story. So in today's video, we'll explore how researchers discovered the GLP-1 hormone in the body, then how two totally different research groups turned that hormone into a therapeutic tool, and finally, how these medications turned into the blockbusters we know today. But to understand how we got here, we need to understand the history of diabetes care. Because after World War II, type 2 diabetes started getting more common, and it was clear that doctors would need a new pharmaceutical strategy to treat this growing number of type 2s. See, usually when blood glucose is elevated, like after you eat, the pancreas releases a hormone called insulin. That insulin binds to receptors on cells all throughout your body, which starts the process of bringing glucose into the cells so that they can use that glucose for energy or store it for later. In type 1 diabetes, the body's immune system destroys the insulin-producing cells in the pancreas called beta cells. As a result, their blood glucose stays elevated, unless they're given insulin some other way. Type 2 is different. It's characterized by something called insulin resistance. The pancreas does release insulin, but different tissues don't take enough glucose into the cell even when insulin is present. As a result, blood glucose stays elevated. But the pancreas can still sense that blood glucose is high, so it compensates by pumping out more insulin. This cycle continues, and over time, the insulin-producing beta cells can fail, which means impaired insulin production on top of insulin resistance. That's why, while insulin can be used for type 2 diabetes treatment, doctors will usually try other treatments first, like lifestyle modification or other drugs. We've had insulin to treat type 1 diabetes since the 1920s, but with the rise in type 2 diabetes after the war, doctors desperately needed new medicines to treat it. This is what made an observation in the 1960s so important, and it was this. Glucose taken by mouth raised insulin production and lowered blood glucose more than intravenous glucose did. That meant that something was happening when the gut processed glucose, and that was signaling the pancreas to secrete insulin. That signal turned out to be a hormone secreted by the gut itself. It became known as an incretin hormone, a term coined back in 1932. So scientists started to wonder if these incretin hormones might make for good diabetes treatments. So they started testing proteins in the gut to see if they could stimulate insulin secretion. The first one to be isolated was called gastric inhibitory polypeptide, or GIP. And it did stimulate insulin production and lower glucose, so it qualified as an incretin. But early studies showed that it didn't lower blood glucose in people with diabetes. So GIP went on the back burner, at least for a while. We'll come back to it by the end of the video. But one of the other potential matches was a hormone called glucagon, which I like to think of as insulin's buddy cop. They both come from the pancreas and work together to keep blood sugar in check. Like, insulin lowers blood sugar when it's too high, while glucagon raises it while it's low. Fun fact, the name glucagon means glucose agonist, meaning it promotes glucose production. Scientists in 1965 found that injections of glucagon led to increased insulin production. And at first that seems non-remarkable. After all, glucagon raises blood glucose, and higher blood sugar usually triggers the release of more insulin. But here's the counterintuitive part. These scientists in the 60s found that insulin rose before blood glucose went up. And that suggested that glucagon itself, not just the elevated blood sugar, was stimulating insulin secretion. So glucagon ended up looking like a good target for diabetes treatment. Unfortunately, studying how these hormones work is tricky, especially in mammals, since the pancreas is such a crowded and complex organ. As you can see from this sample, most of the pancreas is made of acinar cells, which make the enzymes we use to digest food. Scattered throughout the pancreas are small, lighter-colored clusters of cells called the islets of Langerhans. This is where insulin and glucagon come from. Insulin from the beta cells, glucagon from the alpha cells. So instead of studying the crowded mammalian pancreas, researchers turned to animals like the anglerfish. Because unlike humans, anglerfish have separate organs for making digestive enzymes and for making hormones like insulin and glucagon. This finally brings us to a group of Massachusetts-based scientists in the early 1980s. Around that time, researchers had discovered that in order for certain animals to make glucagon, they start by making a larger protein called a precursor. Then the body chops up the precursor into pieces, and one of those pieces becomes glucagon. The Massachusetts group decided to focus on the genes for this precursor in anglerfish. Simply put, a gene is a section of DNA that provides the instructions for building specific proteins that we use in our bodies. More specifically, it tells the cell's machinery how to put together sequences of amino acids, the building blocks of peptides and proteins. So by studying the gene for the glucagon precursor, the scientists hope to learn more about how the peptide was built and if anything interesting happens to the rest of the precursor. And one of the things they noticed was that the precursor had these little regions called cleavage sites. I like to think of them like the perforations in notebook paper. They exist to be broken. Likewise, cleavage sites on a protein make it easier for the cell to clip the bigger protein into smaller pieces, like glucagon. But the scientists found multiple cleavage sites on the precursor, so the natural follow-up question was, what does the rest of the protein break into? Well, in 1982, they published an article showing that the precursor, pre-pro-glucagon, broke into a few different peptides. One of those peptides was a previously undiscovered peptide that they called glucagon-related peptide. And while it might have been a potential incretin hormone, and thus a new diabetes treatment, this was an anglerfish. We need to find out if mammals had something similar. So in 1983, a different group of scientists used hamster DNA to identify the mammalian version of the glucagon precursor gene. But it wasn't an exact match with the anglerfish version. Where the fish had a 34 amino acid sequence, the mammalian version had one that was 37 amino acids long, and then another that was 33 long. They called these glucagon-like peptide 1 and 2, or GLP-1 and GLP-2 for short. Were these incretin hormones? Well, when researchers used the full 37 amino acid version of GLP-1, it didn't stimulate insulin secretion. So at first, it seemed like GLP-1 wouldn't lead to the incretin effect. But then we meet Svetlana Mojsov, a scientist born in what is now North Macedonia. After grad school, she read about GLP-1 and teamed up with Dr. Joel Habner, one of the authors on the anglerfish paper, to study it further. During their research, Mojsov noticed something. If you remove the first few amino acids from the full-length GLP-1 molecule, the remaining peptide looked even more like glucagon. And that made her wonder if the cell might actually cleave off the first 6 amino acids from GLP-1, and the remaining portion was the biologically active form. In the conclusion to her 1986 paper, she proposed that GLP-1 1 through 37, so the full 37 amino acid peptide, might be a precursor to GLP-1 7 through 37, a version of the peptide lacking the first 6 amino acids. So the shorter version might actually be the hormone that has an effect on insulin secretion, which meant that maybe GLP-1 had a sneakier incretin effect than expected. To test this, she measured how well GLP-1 7 through 37 raised insulin in a rat model and compared it to the full-length peptide. And in 1987, they confirmed that yes, GLP-1 7 through 37 is insulinotropic, meaning it stimulates the release of insulin. And they weren't the only ones to show this. Within the year, a research group in Denmark showed that GLP-1 7 through 37 had a much stronger insulin-raising effect than the full-size precursor. So the big takeaway was that, at least in test animals, the 7 through 37 portion of GLP-1 was the active form of the hormone. Later that year, research published in The Lancet confirmed that GLP-1 was made in the human gut, and that GLP-1 levels went up after participants consumed glucose. This meant that earlier scientists stood corrected. GLP-1 could induce the incretin effect after all. But like they saw with GIP, not all incretin hormones become useful medicines. It turned out that GLP-1 only raises insulin secretion when blood glucose was elevated, and that would make it a useful diabetes drug. Since GLP-1 depended on glucose, it reduced the risk of hypoglycemia, or dangerously low blood sugar. GLP-1 also inhibits excessive glucagon release, which prevents it from triggering glucose release from the liver even further. But the big question in the 80s was whether GLP-1 itself could be used as a diabetes drug. Tests in the early 90s showed that when you gave type 2 diabetics an IV infusion of GLP-1, insulin rose and glucose fell, so it worked as expected. But there was one big problem. GLP-1 cleared from the blood extremely quickly. When given by IV, half of the GLP-1 was broken down after about 2 minutes. So GLP-1 by itself wouldn't be a useful drug unless the patient was constantly hooked up to an IV. These days, we know the peptide breaks down so quickly because an enzyme called DPP4 cuts it up and then it's cleared out by the kidneys. This discovery led to a class of drugs called DPP4 inhibitors, but that's a story for another time. So to sum it up, we desperately needed new treatments for type 2 diabetes, and GLP-1 was a promising candidate. The challenge then was figuring out how to make this hormone last longer in the body. One of the strategies was to find a molecule like GLP-1 that naturally lasted longer in the body. And by the early 1990s, scientists had a lead thanks to unrelated research into the venom of the Gila monster. These guys are muscular, venomous lizards found in the American Southwest, known for their brutally painful bite and slow metabolisms. As scientists learned more about the chemistry of the lizard's venom, they noticed that something in the venom triggered inflammation in the pancreas of bite victims. And that made scientists wonder if the venom might have a chemical that interferes with pancreas function. Researchers publishing in 1984 found two potential culprits, what were called helospectin and helodermin. Helo referring to Heloderma suspectum and Heloderma horridum, the scientific name for the Gila monster, and its relative, the Mexican beaded lizard. Helospectin and helodermin are also known as exendin 1 and exendin 2, and it turned out that they both had similar amino acid structures to glucagon, which might have explained the pancreas involvement. So by the late 1980s, start of the 90s, a New York-based scientist named Dr. John Eng picked up on this line of research and analyzed venom samples from the Mexican beaded lizard. And in 1990, he and his team published a paper describing a new peptide that they called exendin 3. But while exendins 1 and 2 were more structurally similar to glucagon, exendin 3 looked more like human GLP-1. So they ran the experiment again, but this time with the venom from the Gila monster, and they found another new peptide, exendin 4. And just like exendin 3, it was structurally similar to GLP-1. Now that raises the question. It looks kind of like GLP-1, but does it behave like GLP-1? And it sure did. When they gave exendin 4 to dogs, it caused insulin levels to rise and glucose levels to drop. This meant that exendin 4 was binding to some kind of receptor in mammals, it's just that nobody knew which receptor. Until 1993, where Eng and a team of other researchers found an answer. Exendin 4 was binding to GLP-1 receptors. This meant that this new peptide from lizards, exendin 4, was binding to GLP-1 receptors in mammals and activating the same physiologic pathway as native GLP-1. But exendin 4 had one very important feature that made it different from GLP-1. That effect on blood glucose lasted for hours, not minutes. Exendin 4 has a half-life of close to 2.5 hours, which would make it a useful medicine. To quote that 1993 paper, quote, "The possible clinical value of the GLP-1 agonist properties of exendin 4 should be seriously considered." Luckily, Eng was already thinking ahead. That same year, he filed for a patent for exendin 4 and started looking for pharma companies to help bring the drug to market. He started by presenting his findings at medical conferences, but he didn't get much traction right away. But then, one day in 1996, he caught the attention of a rep from a small biotech company called Amylin. So Eng licensed exendin 4 to Amylin, who began clinical trials with it. And the results were promising. They found that 2 injections a day of exendin 4 lowered HbA1c, which is a marker for long-term blood glucose control. So this lowered HbA1c was a desired outcome. It also led to a little bit of weight loss. Amylin developed this new synthetic version of exendin 4 as exenatide and got FDA approval for the treatment of type 2 diabetes in 2005. Then, through a partnership with Eli Lilly, they launched the drug under the trade name Byetta. It was the first in a new class of drugs that goes by a few different names. Usually they're called GLP-1 receptor agonists, which means that they bind to the same receptor that our body's GLP-1 does. They're also called GLP-1 analogs, which means that they're structurally and/or functionally similar to GLP-1, and sometimes they're referred to as incretin mimetics because they mimic the job of incretin hormones. Whatever you call them, by 2005, Dr. Eng and the American companies had one solution to GLP-1's short half-life problem. They'd found a different molecule that has the same effect as GLP-1, but naturally lasted longer in the body. But that wasn't the only solution. Because meanwhile, over in Europe, scientists were working on the same problem, but with a totally different approach. Something a little more designer. Now, I've spent the last 2 videos talking about Denmark's biggest pharmaceutical company, Novo Nordisk, so I won't go into too much depth here. The main thing you need to know is that during the 1990s, they were the biggest insulin producer in Europe and the second biggest in the world, right behind Eli Lilly. But for this story, we need to meet a new character at Novo, Lotte Bjerre-Knudsen. As a Danish scientist, Lotte knew all about Novo's work. She wasn't particularly into academia. She was more interested in developing real medicines that could improve people's lives. And while she initially got a job in Novo's enzyme division, she started working on diabetes treatments in 1991. On the day-to-day, Lotte and her team would screen a bunch of potential drugs for diabetes, including compounds that bound to the GLP-1 receptor. But then something unexpected happened. Lotte went on maternity leave in 1993, and while she was away, management at Novo Nordisk restructured certain teams, including the diabetes team. And when she came back in 1994, she was the only scientist left who was familiar with the GLP-1 project. And at this point, Novo Nordisk was more focused on insulin, and their GLP-1 research didn't seem like it was going anywhere, so the CEO, Lars Rebien Sørensen, gave Lotte an ultimatum. In a podcast interview from 2024, he says, quote, "We did give her 12 months to say you got to come up with something more convincing." Meanwhile, other scientists at Novo had come up with something exciting. They developed a method for attaching fatty acids to proteins, which caused the protein to bind to albumin, the most common protein in human blood. This created a bigger, chunkier molecule that wouldn't get filtered out by the kidneys as quickly, causing it to last in the body for longer. In 1995, they published a paper describing their technique and mentioned that it would, quote, prolong the action profile of peptide drugs. And that's exactly what it did. At first, they used their method on insulin molecules, creating longer-lasting insulin analogs. The 1995 paper describes an insulin that looks like insulin detamere, which I talked about in the last video. Now, if Knudsen's team was able to apply this new technique to GLP-1, it might be the something more convincing the CEO was looking for. So they started by attaching fatty acid chains to different positions on the GLP-1 peptide with a goal of finding a variation with a half-life of about 10 hours. That would make the resulting medicine appropriate for a once-a-day dose. And after comparing multiple GLP-1 analogs in pigs, they found several compounds that hit the 10-hour mark, a massive leap forward from GLP-1's original 2-minute half-life. In the year 2000, they published their results in the Journal of Medicinal Chemistry. One of their most promising analogs had a fatty acid tail 16 carbons long attached to a lysine residue toward the middle of the peptide, and an arginine substituted for the usual lysine towards the end. They called this molecule liraglutide. It was structurally similar to native GLP-1 and had high potency, so it went on to clinical trials. During preclinical testing, though, rodents given liraglutide showed an increased risk of developing thyroid tumors. But fortunately, that wasn't the case in monkeys, nor later human trials. By the time liraglutide made it to phase 3 clinical trials, it looked both safe and effective, other than some participants reporting nausea. Luckily, Knudsen's team found that they could minimize the nausea if they started with a small dose of liraglutide, then ramped it up over time, which is a strategy still used today. Novo Nordisk published results from phase 3 trials in December of 2007. They showed that liraglutide helped regulate blood sugar, reduced blood pressure, and led to modest weight loss. It also hit the goal of an 8 to 10 hour half-life, which made it appropriate for daily injections. They applied for approval in Europe and in the US at the same time, May of 2008. It got approved in Europe in 2009 and in the US in January of 2010. Novo Nordisk sold it under the brand name Victoza. And it was clear right away that Victoza was going to hit blockbuster status, or $1 billion in annual sales, faster than expected. Right? Patients who had been taking Lilly's twice-daily exenatide now had a more convenient alternative with once-daily liraglutide. So in the US at least, Victoza started eating into Lilly's Byetta sales in the first few weeks of its release. Now, at the time, Lilly was developing a product called Bydureon, a once-a-week extended-release version of exenatide. But in 2010, the FDA asked them for more clinical data, which delayed its approval. So, and stay with me here, Lilly sold the global rights for both Bydureon and Byetta to Amylin, that small biotech company from earlier. Amylin was then acquired by Bristol Myers Squibb, whose diabetes division was bought by AstraZeneca. So by 2013, AstraZeneca had inherited exenatide. Meanwhile, you've got all these other GLP-1 analogs coming out at the same time. Like Sanofi's lixisenatide, which was another exenatide-based analog, got FDA approval in 2016, but they later withdrew it because it wasn't selling well. Likewise, GlaxoSmithKline's once-a-week albiglutide, basically 2 GLP-1s attached to albumin, got FDA approval in 2014, but was withdrawn in 2017, also due to poor sales. Either way, by the 2010s, there was an established market for GLP-1 analogs as a treatment for type 2 diabetes, and scientists had solved the short half-life problem. The Americans were inspired by nature, while the Danes introduced a brand new molecular technology. But during those preclinical studies, Knudsen's team noticed that animals on liraglutide were eating less than their counterparts, and earlier studies had even shown rats starving themselves to death due to the suppressed appetites. So, as early as the mid-1990s, Lotte wondered if GLP-1 analogs could be weight loss drugs too. GLP-1's viral moment was coming, but it wasn't a given. In April of 2005, the CEO of Novo Nordisk is quoted as saying, "Obesity is primarily a social and cultural problem. It should be solved by means of a radical restructuring of our society. There is no business for Novo Nordisk in that area." Now, I agree with Sørensen that social and environmental factors contribute to obesity, but the, quote, business in that area deserves a closer look, because weight loss medications have their own backstory. It probably deserves its own video. The first drug approved by the FDA specifically to treat obesity was cleared in 1947. This was before drugs had to show safety and efficacy data prior to approval. That drug was desoxyephedrine, which is better known today as methamphetamine. This led to more amphetamine-based weight loss drugs in the 1950s and 60s, but after the FDA started requiring drug efficacy studies in the 1960s, many of these kinds of drugs struggled to show that they actually caused weight loss. The FDA allowed some of them to stay on the market, but only for short-term use, and they needed to come with a black box warning for safety. As a result, amphetamines got less popular by the late 20th century. But then all of a sudden, in the 1990s, a combination of two older drugs exploded in popularity: fenfluramine and phentermine, or what became known as fen-phen. These drugs caused more weight loss together than individually, but then came Redux, a new variation of fenfluramine, and it got super popular, peaking at 85,000 prescriptions a week at one point. Even the media covered it in a positive way at first. But things started to change after a paper came out in 1997 pointing to a possible link between fen-phen use and heart valve issues. And further studies confirmed the link. People who took fen-phen for extended amounts of time, especially more than 24 months, had a higher risk of heart valve problems. Knowing this, the FDA recommended taking the drugs off the market in September of 1997. The company that manufactured fen-phen dealt with some high-profile, very expensive lawsuits at the end of the 90s as a result. This was around the time that Novo Nordisk was beginning clinical trials for liraglutide. So fast forward to 2005, and I can see why the Novo Nordisk CEO wasn't enthusiastic about pursuing obesity treatments. Historically, weight loss drugs were more risk than reward. At the same time, if you could get a drug approved for obesity, the potential market was massive. By 2011, over 500 million people worldwide were living with obesity, and that number was growing. Knudson's group had been looking into liraglutide's effect on weight loss before it was approved for type 2 diabetes. They published their first paper on liraglutide's effects on weight loss back in 2001. And over the next few years, they kept publishing research comparing liraglutide's effects on weight loss to placebos, as well as against other GLP-1 receptor agonists. Working in Knudson's favor was the fact that in the early 2000s, Novo Nordisk didn't have much else in development, so the company changed course and pursued liraglutide for obesity. But where Victoza was 1.2 to 2.8 milligrams of liraglutide, the weight loss formulation was 3 milligrams and went by the not-so-creative name of Lira-3mg. Phase 2 trials started in 2007, followed by Phase 3 in 2011, at which point the interest in liraglutide starts picking up. A set of studies published that year in the Journal of Obesity showed that liraglutide was not only safe, but it led to an average of 6% weight loss in certain patients. At this point, the CEO was starting to come around to the potential of obesity drugs, and the timing couldn't have been better. In the summer of 2013, the American Medical Association released a position statement that officially recognized obesity as a disease that required multiple interventions. The stage was set for weight loss drugs to make a comeback. Novo Nordisk submitted liraglutide for approval as a weight loss drug in December 2013 and got FDA approval a year later. They sold it under the brand name Saxenda in the States. Real quick clarification, liraglutide is the active ingredient in both Saxenda and Victoza. The difference comes down to what the drug is treating and the dosage prescribed. Victoza is prescribed for type 2 diabetes, typically at 1.2 to 1.8 milligrams a day, while Saxenda is approved for obesity and ramps up to a higher dose of 3 milligrams a day. Now, it took some time to figure out how it worked. As Knudsen has pointed out, their new drug application for liraglutide as a diabetes treatment says that they didn't see GLP-1 uptake in the brain. See, while GLP-1 is primarily a hormone, it can also activate certain nerves in the gut and bind to receptors in different parts of the brainstem that lead to a feeling of fullness. The body responds by slowing down gastric emptying, meaning that food stays in your stomach for longer, which contributes to that fullness. So whether it's from the natural GLP-1 hormone or a GLP-1 analog like liraglutide, the response is the same: reduced appetite and less food intake. But this mechanism might also explain some of the gastrointestinal side effects that people experience while on GLP-1 receptor agonists. High levels of GLP-1 signaling to the brainstem can trigger the brain's vomiting center. Fortunately, patients typically build a tolerance to the drug, which tamps down the GI side effects over time. That's why dosages start small and ramp up. After liraglutide's approval for weight loss, Eli Lilly introduced dulaglutide, a GLP-1 analog for type 2 diabetes treatment. And unlike liraglutide, which is a single GLP-1 molecule hooked up to a fatty acid, dulaglutide consists of two modified GLP-1 analogs hooked up to a fragment of human antibody. This design lets it resist breakdown by the DPP-4 enzyme, which allowed for once-a-week doses. Lilly sold it under the brand name Trulicity, but Novo Nordisk wanted a once-a-week injection too. And to do this, they decided to build on their albumin binding strategy from liraglutide's development. But they needed to change something, because they learned that while longer fatty acids increase the peptide's ability to bind to albumin, which increases its half-life, that came at the cost of affinity to the receptor, or how well the drug binds to its receptors, and that led to worse potency. The challenge then was to find a molecule that would bind firmly to albumin, but also to GLP-1 receptors. Their best candidate was called semaglutide. It had a GLP-1 7 through 37 sequence, which was modified in 2 different amino acid positions, attached to an 18-carbon fatty acid chain via a very important linker. But even before it hit the market, semaglutide was getting attention. In a Novo Nordisk-sponsored trial published in the New England Journal of Medicine, patients with type 2 diabetes treated with semaglutide had fewer heart attacks, fewer strokes, and died from cardiovascular events less frequently than the placebo group. This paper has been cited over 6,000 times, which means it was super influential. Now, this was 2016, 2017, which was around the time that Novo Nordisk's patent on liraglutide was about to expire. This meant that other drug makers would be able to start making their own versions of the drug. And in 2017, an Israeli generics producer, Teva Pharmaceuticals, applied for FDA approval for a generic liraglutide. Novo Nordisk saw this coming, but they wanted a little more time to transition their customers to their new drug. So they reached a settlement with Teva where Novo Nordisk would extend their market exclusivity on liraglutide through 2023. That would give Novo Nordisk time to ramp up marketing for their newly approved GLP-1 drug semaglutide, what they sold under the brand name Ozempic. And market it they did. In 2018, they launched a massive campaign for Ozempic. This is when I remember first hearing that commercial would be, Now, at this point, Ozempic was still only approved for type 2 diabetes. But during its clinical trials, researchers noticed significant weight loss in diabetic patients. Like with a 2 milligram dose a week, 40% of participants lost at least 10% of their body weight. So while diabetes trials were ongoing, Novo Nordisk started testing higher doses of semaglutide for obesity. Phase 3 clinical trials were expected to finish by the end of 2019. But even before official approval, doctors were prescribing Ozempic for weight loss anyway. See, in the US, doctors are allowed to prescribe a drug off-label, meaning for a condition it doesn't have FDA approval for. This is when hype for GLP-1s really start building in the general public. Because among other things, the clinical trials of semaglutide for weight loss were looking extremely promising. Participants lost about 12 to 17% of their body weight over a year of treatment, compared to about 8% with liraglutide. Yes, there was the issue of weight loss plateauing or gaining the weight back, but as long as the trial participants were able to stay on semaglutide, they tended to see the intended weight loss. There was also still some nausea and GI symptoms, which sometimes even caused the participants to stop treatment. In June of 2021, the FDA officially approved semaglutide for weight loss. Novo Nordisk put it on the market as Wegovy. And since they were already producing semaglutide at a large scale, they had it for sale in American pharmacies within the month. Now remember, by 2021, doctors had already been prescribing Ozempic for weight loss for years. And at the same time, some major American insurance companies formally decided that they would reimburse for Wegovy, which made it more accessible. The result was that Wegovy got more prescriptions in its first 5 weeks of sales than Saxenda did in its first 4 years. And while Ozempic and Wegovy were exploding in popularity, Eli Lilly was working on something new. They already had a weekly injection with Trulicity, but they wanted to experiment with something a little different. The result was called tirzepatide, a dual agonist that stimulates 2 different receptors, GLP-1 receptors and receptors for that incretin hormone I mentioned earlier, GIP, although by 2022 it had been renamed glucose-dependent insulinotropic polypeptide. In the spring of 2022, Eli Lilly released tirzepatide under the names Mounjaro for diabetes and Zepbound for obesity. Some of the trials with tirzepatide showed over 20% body weight loss in participants with obesity. So, we've got this pent-up demand from years of off-label use, and now FDA approval for obesity, a condition that millions of people have. It was already prime conditions for a shortage. And then TikTok happened. From 2021 to 2023, information about GLP-1 analogs hit the general public hard. Celebrities, influencers, and everyday people started sharing their experiences online. This became a big enough phenomenon that academics wrote journal articles about it. And according to a non-academic article on trackdrugs.com, The Ozempic hashtag on TikTok grew from around 2 million views in 2021 to well over 1 billion in 2023. But just as demand was exploding, the supply chain hit a snag. In October of 2021, the FDA visited one of the facilities that Novo Nordisk was using to make Wegovy. According to the 2023 book about Novo Nordisk, the visit resulted in, quote, very harshly worded criticism and a shutdown of the production plant. So in 2022, between the social media hype and the factory shutdown, demand for semaglutide outpaced supply. As a result, the FDA declared a shortage of Wegovy in March and on Ozempic in August. Lilly's tirzepatide followed onto the shortage list in December, and Novo's older liraglutide followed in July of 2023. Now, the FDA defines a shortage as a, quote, period of time when the demand or projected demand for the drug within the United States exceeds the supply of the drug. And while I couldn't find the exact quantity of the shortage, the important thing to know is that new rules apply in this situation. Because as long as a drug is in shortage, FDA rules allow special pharmacies called compounding pharmacies to manufacture the drug. These are facilities with the ability to make bespoke medicines, usually for individual patients. For instance, if you have an allergy to one of the ingredients or need a modified dosage, compounding pharmacies can make that happen in a way that a large-scale factory can't. Importantly, though, the compounded version does not need FDA approval. Novo Nordisk has highlighted this fact in advertisements, like this one, which I'm pretty sure is meant to mimic the style of Hims, an online semaglutide seller. Speaking of the name brands, semaglutide and tirzepatide were both under patent at this point. So what are the compounders actually selling? The short answer is that compounding pharmacies are allowed to make patented drugs when the FDA declares a shortage. But the compounders couldn't actually buy pure semaglutide or tirzepatide from the original manufacturers, so they had to resort to less regulated sources. Like some compounders made salts of semaglutide, like semaglutide sodium or semaglutide acetate, and some used research-grade semaglutide, which isn't held to the same purity standards as its pharmaceutical-grade version. It even got to the point where the FDA issued a warning saying, hey, just reminding y'all that these are different from the active ingredient that we approved. As you can imagine, both Novo Nordisk and Lilly wanted to fix the shortage and take back their market share. So both companies spent 2023 and 2024 building factories dedicated to GLP-1 production. Tirzepatide came off the shortage list on October 2nd, 2024. On February 21st, 2025, semaglutide followed. In both cases, the FDA gave compounders a few months grace period to wind down production without penalty. Liraglutide was a little different though. Novo's patent extension settlement with Teva Pharmaceuticals finally came to an end and allowed Teva to manufacture an authorized generic version of Victoza in June of 2024. By the end of the year, a British drug maker named Hikma Pharmaceuticals followed with their own generic version. But even during the shortage, drug companies were still working on new GLP-1s. Like Eli Lilly is developing retatrutide, a triple agonist that binds to receptors for GLP-1, GIP, and good old glucagon. As of the time of filming, it's in phase 3 clinical trials. Lilly also acquired an oral GLP-1 receptor agonist that they're calling orforglipron. It's a small molecule, not a peptide, so unlike Novo Nordisk's oral semaglutide Rybelsus, it makes it through digestion fairly intact. Early clinical trial data in type 2 diabetics showed weight loss and blood sugar reductions on par with semaglutide. And an effective GLP-1 pill would also be useful because it's easier to get people to take pills than injections. Now, a ton of the hype around GLP-1s is based on what people expect them to do in the future. Like they'll end obesity or Alzheimer's and they'll become the miracle cure of the 21st century. And maybe those will happen, maybe they won't, but we can still take away some lessons now. Takeaway number 1, the early GLP-1 research in the 80s and early 90s was truly creative science. Like, once we knew that GLP-1 and GLP-1 receptors existed, scientists used different routes to find agonists for that receptor. John Eng's team used Gila monster venom to make exenatide, while Lotte Knudsen's team used that special albumin binding strategy. And both of them benefited from the recent accessibility of recombinant DNA to make hormones. Takeaway number 2, timing was everything in this story. This is pure speculation now, but had Novo Nordisk tried to market liraglutide for weight loss so close to the fallout from Fen-Phen, I doubt that patients would have swarmed to it like they have. Because even though they work totally differently, Fen-Phen and Redux spooked a lot of folks away from the idea of weight loss drugs. So instead, by waiting and studying the product for a few years, the memory of Fen-Phen faded, and Novo had a global customer base who was ready to give weight loss drugs another chance. But the timing of TikTok might have been even more impactful. Right? Americans understand the typical pharma advertisement at this point. It's enough of a trope that SNL has a parody drug commercial every other week, it seems. But when you hear people talk about Ozempic on TikTok, it doesn't feel like an advertisement sometimes. It feels personal. It feels like that person is sharing their experience with a product, like it's a restaurant or a book they're recommending. TikTok feels like word of mouth, but has the reach of the entire internet. Plus, semaglutide is unique within the world of pharmaceuticals. It's a drug that can be sold like a regular old consumer product since obesity is so common. Although it would be wild to think that the TikTok phenomenon could apply to an antibiotic or a bronchodilator or something with a more niche patient base. Takeaway number 3. The financial success of GLP-1s changed the pharma industry's appetite for weight loss drugs. Pun intended. These days, whether it's a GLP-1 analog, a triple agonist, or something entirely different, just about every major pharma company is working on some kind of weight loss drug. So regardless of what happens with GLP-1s in the future, they'll go down as the drugs that put weight loss back on the table. This video has been one of my most requested videos for literally years, and I'm thrilled to finally share it with you. But before you go, I've got some exciting news. From now on, you can find my videos early and ad-free on Nebula, the indie streaming platform made by creators for creators. You probably sat through, 4 or 5 ads to get here? Well, on Nebula, there are no ads. You can watch videos uninterrupted for quite literally hours. My catalog is on there, plus bonus videos you won't find on YouTube, like one about a Nobel Prize-winning scientist who thought vitamin C could cure cancer, and another about how nobody knows where Neosporin comes from. But Nebula is home to hundreds of other creators you probably already love. There's medical creators like Medlife Crisis and Chubby Emu, as well as folks you've seen on this channel before, like Knowing Better and Mia Mulder. Plus, there are tons of Nebula originals, content you won't find anywhere else. I've been catching up on Lindsay Ellis's latest video essays, including a deep dive on The Lord of the Rings and a documentary about the comeback of Guy Fieri. The girl's got creative range, I tell you. But what I love about Nebula the most is the curation. Like, all the other creators are so smart and so creative that whether it's a toxicology case study or a satirical debate, I know the video is going to be high quality and worth my time. So if you want to check out the finest streaming platform on the internet, go to nebula.tv/Patrick Kelly. That'll get you 40% off on an annual subscription, just $36 for a full year. You'll be directly supporting me and other creators and helping us make cool stuff. Again, nebula.tv/Patrick Kelly. Thanks for watching, y'all. Go sign up for Nebula.